One of the key breakthroughs there is called embeddings. You can take a word and turn it into a vector, and you can do it in a way such that it preserves the semantic meaning and relation. And you can do vector algebra. One cool example is if you take these vectors, you do king minus man plus woman, the result it gives you is the vector for queen.
You're saying like there's an independent field of study in mathematics, vector algebra, and the researchers realized that if you were to create these embedding,
yes, you could convert words to vectors. Yeah, you can use the
algebra that they have figured out over here, and this pattern seems to repeat a lot in science in general, right? Like there'll be some independent field of study somewhere, and then there'll be like some emerging tech somewhere, and then they realize, oh, we could like use all this stuff from this other field of studies.
Hey, welcome to the Art and Science of AI. You're listening to Season 1, which we recorded in May 2023 as a continuous 3-hour-long conversation. Season 2 is now live, so if you're enjoying this discussion, please subscribe for new episodes every week.
So we wanted to talk about generative AI, right? Yeah. So we can next move into like how text is dealt with.
Okay.
So first question is, how do you encode text, right? Like in this, the first question we had about images was, how do you encode an image?
Right.
And then we said, okay, we look at each individual pixels.
Yeah.
And each pixel is encoded in RGB value if it's color, or like 0 to 1 if it's grayscale. Right. Now, how do you encode text? So this is actually very complicated. There's 2 main steps to encoding text.
Wait, that's not hard, no? Like encoding of text is something that computer scientists have, like ASCII and like binary, all that is encoding of text, no?
Yeah, sorry. I mean to say like encoding it in a way that can preserve some semantic relationships.
Oh, I see what you mean. How do you infer meaning from
Yes, exactly.
Because so far it's only been manipulation of bits.
Yeah, you can arbitrarily come up with some encoding that doesn't like, but the key is, can I come up with a way of encoding text that preserves semantic relationships, the meaning of words.
Right.
And I think one of the key breakthroughs there is called embeddings. It's basically word vectors. It's a method of turning a word into a vector. Like how we take an image here and turn it into a 784 length vector. Similarly, you can take a word and turn it into a vector. And you can do it in a way such that it preserves the semantic meaning and relationships.
Give me an example if you can. Or...
Yeah, so that's actually in the next slide. So for this is called word embeddings, okay? Right. So for each word is turned into a vector like this. In this case, these are the dimensions of the vector. There are like 7 dimensions, but in the case of an actual model like GPT-3, I wrote down how many...
Oh, it looks very similar to like a concept that Google has and maybe others have as well.
The embedding dimension in GPT-3 is over 12,000. So this thing, the 7 that you have here, they're like 12,000 dimensions.
Yeah, like just by seeing your first example, it says cat, and it says a cat is a living being. It's a feline, human. Oh, well, it's not those things, but like you have these groups. So like internally at Google, we have this thing called a knowledge graph. I don't know if it's internal, but like we have a concept of knowledge graph where like on Google search, a lot of times you will see a knowledge panel when you search for something. So let's say if you search for Barack Obama, there'll be a special result where it'll be pictures of Barack Obama and it'll say American president. Like it has all these things. Yeah. So for example, the way to do that is by having a knowledge graph where it knows that this person is an American president. Like there is a knowledge graph. So every entity has a graph with many connections.
Okay.
Right? So it sounds like a similar...
Yeah, I think they could be related. I don't know much about knowledge graph, but it's possible that they are related concepts.
Yeah.
Basically, what's happening here is where for each word, you're figuring out like what other words and what context does it appear in.
Right.
That's what an embedding is.
Okay.
And you can set a number of dimensions for an embedding. In this case, there are only 7 dimensions, and they're all like very interpretable, which is unrealistic. In reality, there are going to be thousands of dimensions and you can't really interpret them. But the key point is like what you're doing is figuring out this word, what context does it appear most frequently in? And that's what an embedding is. It's saying in these contexts, it appears more frequently. So you go through your entire corpus of training data and figure out in which context word appears more versus less.
So yeah, in this case also, you could just give it a lot of unstructured data and then it can figure this out. Meaning you give it all the text that's ever been written on Reddit, which is a lot.
Even more. Like trained on 3 billion or some number of billion tokens. I
don't know what tokens is, but I see what you mean. Meaning you can keep it super unstructured and it'll create an embedding out of whatever data you give it. And will that happen for every single word within that training data?
Yes, absolutely. So GPT-3 has the vocabulary size of GPT-3 is 50,000 words. And the embedding dimension is about 12,000. So in fact, that leads to it having
Wait, that means every word has 12,000 columns and its relation, like how frequently does it come with those 12,000 words? That's insane. So what is that?
50,000 multiplied by 12,000 is about 600 million. That's the number of parameters. But that's only like the beginning. Remember, it has billions of parameters. So every number here is a parameter of the model. The model can then find what is the right value for this parameter. So right here, there are going to be, as we said, 600 million plus parameters with GPT-3. But before talking about parameters, let's think about what is the value of creating these word vectors. As I said, they preserve the semantic relationships between words and concepts. So to give you an example, look at this graph here. This is a visualization of these word vectors for man, woman, king, and queen. And what you can do is you can do vector algebra. Probably you learned this in high school, like vector algebra is you can add and subtract vectors from each other. And one cool example is if you take these vectors, you do king minus man plus woman, the result it gives you is the vector for queen. You do father minus man plus woman.
You're saying like there's an independent field of study in mathematics, vector algebra. And like the researchers realized that if you were to create these embedding,
you could convert words to vectors. You can use the
algebra that they have figured out over here. And this pattern seems to repeat a lot in science in general, right? Like there'll be some independent field of study somewhere, and then there'll be like some emerging tech somewhere, and then they realize, oh, we could like use all this stuff from this other field of study. Sounds like that's what happens here.
I think one of the earliest times this happened was with Descartes in the 16th century when they got really stuck with geometry and they realized that geometry and algebra could be related. This happened with what's called Cartesian math. Descartes in like the 16th century realized that there are a lot of problems you're having in geometry that can't be solved. But once you map geometry onto algebra, like you say, the geometry is just like algebra on like a graph. You can solve a lot of like geometric problems that you previously couldn't solve by converting them to algebraic problems because there are a lot of results in algebra that directly you could apply to geometry.
Yeah, I mean, I'm sure you would appreciate that because you studied logic, but like that's what sort of the genesis of Boolean logic, right? Some guy was independently creating Boolean logic for, I think his pursuit was to like prove the existence of God. George Boole. No, I don't know.
It could be. I don't remember.
Some interesting story. Maybe I'm butchering it, but like his pursuit was to like prove God or something, and he was trying to find out, oh, I'm going to take all these statements from Bible and then I'm going to apply some logic and then drive conclusion. And I think he discovered Boolean logic. And then over here, these people who are dabbling with computer science are like, oh, we could use this existing field of study and look what we've made. So it looks like something similar is happening here.
Absolutely. And I think ultimately all of it is just mathematics. Like there are a lot of results in mathematics, like a lot of relationships that people, it's about encoding different objects into a mathematical formulation and then being able to like leverage those results and relationships. And that's exactly what's happening here. We know how vectors are related to each other. Once we convert words to vectors, then we can leverage those.
This is very cool. Like
those relationships.
You're saying that if you were to do all this, then you'll come up with vectors of man, woman, king, and queen. And if you apply that vector logic, like the way you did,
it preserves these relationships between them.
Like because that's how we think about it. It's like, okay, man, woman minus that, then that's a king. Well, that's cool. Okay,
absolutely. So then this is the first part of how this is the encoding problem. We talked about how to encode our input into features, right? That can go into the model. For images, it was the pixel values. For words now, you start with first tokens. A token is like an individual word. Think about it that way. Like cat, kitten, these are tokens. That's step one.
Is that a common parlance in the...
Yes, in this. So in fact, if you go to GPT 3 or ChatGPT, it'll always describe its limits in terms of the number of tokens. So the context size is one of the important limiting factors of GPT. With GPT-4, I think the context size is
25,000. Huh?
No, it's 4,000 or 8,000 tokens. And then there's an expanded version that's like 32,000 tokens, but that hasn't been released yet, which means that the total of the input and the output that it can generate at max, it can have 4,000 tokens.
Why don't they use words like words? Like with words?
Yeah,
What's the difference between words and tokens?
That's a good question. I don't know the exact answer. I think there's a difference. Like, for example, the word man and the word men are the same, two different words, but they're the same token.
Oh, I see what you mean.
Yeah.
Oh, okay.
So like man, or if you have like man, man's, man apostrophe s, like plurals and all that. So those are like concatenated into the same token.
Right. Okay.
Because ultimately, whether it's man or like man's, they're
but actually, why are they treated the same way in the model? Because they have different semantic meaning, no? Different semantic meaning, but they have different usages.
That's true. Actually, I don't know the exact. I could look it up, but I don't know the exact relationship between words and tokens. I know that it's not a one-to-one relationship. There are some things that are bundled together, like different words into the same token.
Okay.
And sometimes the same word is multiple tokens based on if a word has two meanings, like then those are separate tokens. So So yeah, we were talking about.
So actually, if you backtrack a little, I want to go stick to our story.
Yeah.
Classical ML goes to classical approach to programming, then classical ML, then neural nets, then deep learning, and now we're moving to like generative stuff.
This is still deep learning. Yeah, but this is now a basis for like generative
to analyze text and how to encode text.
Yeah.
So vector algebra came to the rescue.
And you can put it in the same thing here. Again, you can put all those vectors here and you can run it through this. And you could run like a classification model like this, where instead of like 0 through 9, suppose you have your spam problem. You can have two classes, 0 and 1, spam, not spam. You can put those inputs here, all those vectors. It's a little more complicated because you're just putting the individual vectors there. You need a way to get the sequence and order and things like that. So the architecture becomes a lot more complicated, but the basic concept is the same. You have a way to encode text. You can now feed that into your machine learning models, and you can use it to perform tasks like classification, prediction. So that's how you encode text, and that's how that fits into like deep learning. Yeah. Yeah. And then so I want to go back to this thing here. So we talked about like features, right? And now let's think about what are some of the other things that are going on for a language model.
Actually, we didn't even come to language model. How do we get to language model? So what is a language model?
Yeah. I guess now if you... So
this is a model.
Yeah, exactly. So then let's talk about like what is generative AI, right? Like, generative AI is just types of models that create new data that mimic characteristics of like the training data. So it's like instead of doing a prediction task, the goal is generate something new that's similar to what was in the training data. Images or text. The most popular use cases are images and text. There's also audio and video, which are like more complex, and I think they're a little harder to understand.
Yeah, but if it's actually it's mind-boggling. Like with Mid-Journey, it's able to like imagine new image. I mean, you need a prompt, obviously, but it's crazy. Like the output is so aesthetically pleasing, and it never existed before. It's like something that our minds imagine. Like, how the hell does it do that?
Yeah, that honestly, even I don't understand. It's a combination of images and text. I mean, through using the concepts that we discussed. But yeah, I don't exactly understand how Mid-Journey specifically works. It's a combination of the image.
Yeah, but like just general idea of like, forget Mid-Journey, but even GPT-4, for example, the output it has, it's not so. For example, I'll go back to my first example where I was asking, it's like, oh, my baby girl, I want to start solid foods. Its answer, it's not as if it's copy pasting that answer from like the billions of training data that is found somewhere. Like, oh, I found this Reddit thread that someone was asking the same thing, so I'm going to copy paste. It actually uses the context in which I've presented the question and then answers accordingly. So it's like It's like us, like this conversation.
Yeah.
If you take all the words, it's a novel thing. It's never happened before. That's what we do, right? How is this machine able to do that? I don't like. That's the magic for me.
So yeah, I don't know if I'll be able to answer exactly that. I hope like we have some building blocks that we've built up so far, and we can talk about specifically how ChatGPT is trained.
Right.
There are a couple of more concepts that we can cover there, and then we can discuss.
Yeah. So this is model. I think I have like based on what you explain, I'm getting a good understanding of this. Then what is a language model? What is a large language? Because I keep hearing this word LLMs, LLMs everywhere. I don't know what that means.
A language model, we talk about generative models. Generative models' goal is to generate something new that resembles the training data. Language model, the goal is just to generate text that resembles text that was found in the training data. So the very basic function of a language model is to predict the next word given a set of words. So if I give it a string of like, some 10 words, it'll predict what is the most likely next word to come out of it based on what it learned from its training data. That's at a very base what a language model does. And you can extend that to, instead of predicting the next word, I can say predict the next 100 words, or predict that's the token size. That's what we were talking about with
given
GPT.
A word.
You can say anything so when you go to ChatGPT, you can type in just one word if you want and press enter and it'll generate something.
That seems ineffective, no? Like it should be given like you're saying it could work even with a word.
Yeah.
But obviously the more input, the better. Like
the more input you
predictive
give it, the
power
better.
it'll have.
But all it's doing is like if you say, sorry, I had one example here. If you have a word like, I don't remember, like this is a blank, okay, then it'll look at all the past instances in the training data where this combination of words existed. This is a followed by what was the next word there, and look at what is the most probabilistic outcome of that next word based on my training data.
Okay.
That's the first thing it does. And then if you ask it what's the next word, again, it'll say, now the context is this. I've put it into my context. What's the most likely next word to come out of it? So what it's doing is trying to predict the next word based on its training data. And this is the way the training data is encoded in the model. And the architecture of GPT-3 is extremely complicated. I have like this slide on it. I cannot explain it to you. Unfortunately, it is too complicated. But I think the key thing I want to emphasize is there are multiple loops and layers of like feed forward network. This thing that here, this says feed forward network. What that is this thing. This is called a feed forward network.
Right.
This is the most simple kind of like neural network where everything is just going in this direction. There are way more complex neural networks. They're called like recurrent neural networks or long short-term memory networks that have more complex architectures. But what is happening here is there are a bunch of different neural networks that are combined together. They're probably like, like n number of different layers of neural networks here.
Right. So you're saying that like if you go back to that one neural network slide where you have like the 784 pixels predicting. So with GPT, the level of complexity is so high that it has many of such neural networks.
It has n number
and the hidden layers between them is also insanely large.
Yes. And that's how you get to 175 billion parameters, because as I said, the starting point for the number of parameters is here, and that's actually 617 million, because we discussed that there are 50,000 vocabulary words, and then there are about 12,000 embedding dimensions.
Right.
So that itself is 617 million parameters. And then that's going through and getting multiplied by, remember how when we talked about here, each layer was getting multiplied several times. So similarly, how this 784 led to 13,000. So in GPT, we're starting with 617 million instead of 784.
So help me understand this, just because it's like mind-boggling the amount of computation that is going through this. So every time I'm asking a question to ChatGPT, like it must be doing an insane amount of computation to answer.
Yeah, so we need to separate two parts
that only so
machine learning. There's training and inference.
That's what I was going to come to.
Yeah.
Is the computation only required for training, and once you have trained the model, then the answers are not very computationally intensive?
No, again, like going back to this example here, the training is the process of finding the parameters.
Right.
It finds that 150 are the right parameters. That's what training is. And in the case of this neural network, training or learning is finding the right weights and biases. That's finding the right value for all these 13,000 parameters. That's training. Inference is given a new training example or a new example, calculate all these 13,000 parameters and output the final value. That's a much simpler computation.
Right, but in all of these previous examples, the final value was limited, right?
Mm-hmm.
It was either like a concrete, discrete, yes, orange, yes, no, apple.
Yeah.
Or it was like a set of values in the home value price, which could be like between 1 and infinity, but it's still like a arithmetic, right?
Yeah.
But in case of generative AI, it's still like a combination of words, but it's...
No, remember, it's multi-step. At every stage, it's just predicting what is the next most likely word. At every step is just one prediction that's coming out.
So you're saying it's actually as simple as that. It's just predicting the next... So
that's what a language model does. You give it some input text, it takes this text and it says, what is the next most likely word to come out of that? First, it does that. Then now that word that it output...
It's always a word, like literally. It's just
a token, yeah. Then that word becomes part of the context. And then it says, now given this entire context, what's the next most likely word?
To this day, the way ChatGPT or ChatGPT-4 is working, it's like at the algorithm level, it's only predicting the next word every time.
Yes, it's only predicting the next word every time. Yeah. That's the basic language model. There's some like reinforcement learning on top of that too. Input human preferences and stuff for like the style of response it gives you. But yes, at every stage, it is just predicting the next word. Given a context, what is the most likely next word to come out? That's the prediction task. And that's what the
it doesn't even consider, okay, here's the next 4 or 5 words. Because a lot of times your next word is not just influenced by the previous words or the context, but you might choose what your next word should be based on what the other following words could be as well, right?
Yeah, that's how a human would do it, but that's not how
maybe that's the next
GPT
evolution.
Yeah, I don't know exactly how that would happen, but right now a language model just predicts the next word. And there are a couple of steps in this that I wanted to talk about. So how ChatGPT... So this actually talks about how GPT-3...
Move the mic a little bit closer. Yeah.
This is GPT-3, how it's trained. The output of this...
Actually, before we jump into all this, what does GPT stand for? Is that
it's Generative Pre-trained Transformer. Or it might be generalized pre-trained transformer, but I think it's generative. But the transformer is this type of architecture. It's the model architecture, like how we had linear regression, and then there was feed-forward neural networks. Transformer refers to this type of architecture. Generative just means like it's generating text. Pre-trained refers to the fact that it is trained and it has these parameter values already fixed.
Okay. And is that something that OpenAI came up with, or like GPT is like a general term, like everyone can have their own?
They just came up with their own name.
So when I hear the word GPT in the wild, it's always to do with the OpenAI's GPT. Like it's not that Google will have its own GPT and Facebook will have its own.
No, they'll have different names. And that's actually an interesting question, because recently OpenAI has been trying to enforce their trademark on GPT, because a lot of people have been publishing applications with the name GPT in it, and OpenAI wants to avoid this name becoming genericized.
Right.
So
too bad. Cat's out of the bag.
Yeah, I mean, I think there's some legal methods they can use. There's this, I don't know, trademark law is very complicated. There's this thing where if people are using this word in a generic way, then you can't enforce that trademark anymore. So I think Xerox was one example. People started using Xerox in a generic way. It's like, I'll Xerox this paper.
Airbnb is another one.
Yeah. So in those cases, you lose your trademark ability.
Yeah.
So I read recently that
there are pros and cons, because it's nice to be in a position where your company's name has turned into a verb. Like, I'll Airbnb it, I'll Google it, I'll GP it, maybe.
But I think they don't want to be associated. Like, if I make an application called Chaos GPT exactly.
You don't want to be associated.
They don't want to be associated with that. So But okay, let's just finish this thing. So this is GPT-3. ChatGPT is one step beyond GPT-3. So this thing here is initial language model. That is like GPT-3. Okay.
Right.
It's what it starts with. And then it does this thing called reinforcement learning based on human feedback, and it comes up with a reward model. What that is not just predicting the next word, but like it's taking human preferences into account. So the humans evaluate a bunch of samples of prompts and responses. And there are a bunch of like, basically they hired like contractors to evaluate like prompts and responses, rate, is this a satisfactory response or not? And that's the second step on top of the language model. All it does is predicts the next word based on the training data and the model. It just predicts the next word and then the next word, and then it produces a string of text. This process, it's called RLHF, reinforcement learning with human feedback. That's like the next innovation on top of language models, where they input human preferences into the style of response the GPT gives you. So it's not just about predicting what is the most likely next word, but you have to predict the most likely next word that is like liked as an output by human beings generally. So you can't give output that's...
Help me understand this. So GPT-3, it doesn't have that human feedback.
No.
But is it gibberish that it produces? Or is
no.
Is it like too rude? And you need human feedback to like make it more polite. Like
yeah, it's like either too rude or it's like not super context aware. Like it's just not the style. Yeah, actually, I don't have a good example of like what kind of response it
but
gives
it's not
you.
Gibberish.
No, it's not gibberish at all.
GPT-3 could very well work as ChatGPT. You might not like it, but it's going to be legible.
It's not conversational. It's not intended to be, because the way GPT-3 is trained is like you gave a snippet of text. It's like that text was in the middle of an article, and then it's predicting like the next text from that. That's not conversational. So this process just makes it conversational. That's all.
Right. Okay.
GPT-3 is like normal text. What it can predict the flow of text,
right?
But it's not optimized for conversational text.
Right. So the innovation with ChatGPT was using GPT, which is a language model, and make it more conversational, which is what I'm enjoying.
Yes, exactly. Okay. In fact, it's not, the model itself is called Instruct GPT, which is supposed to be like taking instructions and fulfilling those instructions. So yeah, but ChatGPT is based on that basically.
Okay.
Yeah. So basically that's everything I wanted to cover on language models and AI. I think I just have one or two more slides that talk about now what this means now, how you can use GPT to like build applications and do cool things.